In this part, we'll look at policy gradient methods. Policy gradient methods are model-free, policy-based reinforcement learning methods. Like policy iteration, they solve directly for a policy, but unlike policy iteration, they don't assume that the model is known. We'll look at the policy gradient theorem, which makes policy gradient approaches possible. We'll also study the reinforce algorithm, which uses the policy gradient theorem to do policy improvement. We'll then study actor-critic methods. Actor-critic methods are a combination of policy-based methods and value-based methods that overcome a key limitation called sample efficiency with approaches like reinforce. After this section, you're expected to be able to explain the policy gradient theorem, apply policy gradients and actor-critic methods to solve small-scale MDP problems manually, explain how actor-critic methods overcome the sample efficiency problem of standard policy gradient methods, program policy gradients and actor-critic methods to solve medium-scale MDP problems automatically, and compare and contrast policy-based reinforcement learning with value-based reinforcement learning. Let's get started. So let's start out by giving a bit of intuition behind policy gradient methods. In policy gradient methods, we approximate the optimal policy by executing actions and responding to the rewards that we received in episodes. We can do this provided that the policy we're trying to optimize has two properties. The first is that the policy is differentiable with respect to its parameters. If the policy is not differentiable, we can't calculate the gradient of it, so we can't apply policy gradient techniques. The second property is that the policy needs to be stochastic. Recall from earlier that a stochastic policy specifies a probability distribution over actions rather than giving us an action for a state. It's typically of the form where the policy returns the probability that we should play action A in state S. The reason we need this probability distribution is because we're going to use the policy to explore and exploit during the reinforcement learning process. The goal of policy gradient reinforcement learning is to approximate the optimal policy into a policy pi theta S of A, where the theta is the parameters for our policy. In policy gradients, we're going to use gradient ascent, which is the inverse of gradient descent, in order to find the best parameters, theta, for a particular MDP. But importantly, the method we use to represent this policy must be differentiable and stochastic. The objective of a policy gradient method is to find a policy that maximizes the objective J for parameters theta, where theta is the parameters of our policy. This objective is to maximize the value that we get by following policy pi with parameters theta from the initial state of the MDP S0. So here, theta is the vector of parameters of our policy pi that we're going to adjust using our policy gradient approach. V itself is very computationally expensive to calculate. So we use policy gradient algorithms to approximate it, similar to the way we do things with Q-learning and SASA, where we approximate Q functions. We search for a local maximum in J, theta, by ascending the gradient of the policy with respect to theta using episodic samples. In other words, we run lots of Monte Carlo samples the same way we do with Monte Carlo reinforcement learning, and we use those samples to upgrade our policy. Given the policy objective J, the policy gradient of J with respect to theta is written like this, where we use, again, this upside down triangle to represent the policy. This can be calculated by taking the partial derivative of j with respect to each of the parameters in theta, like so. And thus the gradient is calculated as the vector of all the partial derivatives for each of these parameters in theta. So if we look at this, we're saying take the partial derivative of j with respect to theta 1, then theta 2, then theta 3, all the way down to theta n, where n is the number of parameters that we have. We're going to use this gradient calculation in order to update the theta parameters in the direction of the gradient, which will improve our policy. The general algorithm behind policy gradients is the same as policy iteration. We evaluate our policy and then we improve it. When we improve the policy, what we want to do is we want to sample an action, see how good it is, and then follow the gradient towards the optimal set of theta for our problem. For this, we use the gradient and we update the weights of our policy using the following rule. Remember that theta are our parameters. Theta so we want to update our parameters towards the optimal j of theta. So similar to Q-learning, we have a learning rate alpha, which is used to weight our new information alpha against our old information 1 minus alpha. And in this case, the alpha dictates how big the step should be in the direction of the gradient. The question is, though, what is this expression here? Because we don't know what it is initially, we don't know which direction to go. The policy gradient theorem says that for any differential policy, pi of theta, state S and action A, that the gradient of j theta is equal to so this expression is the probability of selecting action A in state S according to our policy, and the expression, the log of this, tells us how to change the weights theta. Effectively what it's saying is we should change the log probability of selecting action A in state S against the value of that action, Qs of A, where Q is some quality of executing action A in state S. We don't actually know what that value is, but we're going to look at how to approximate it a bit later. So therefore this expression says that if the quality of selecting action A in S is positive or high, then we should increase this probability here. Therefore, when we take the gradient of this expression, what we get back is the vector that most increases the probability of selecting action A in state S in future episodes. If the quality of selecting action A in S is high, then we'll increase this probability more than if it's low, and if it's negative, we'll decrease this probability. We won't go into detail about how to calculate gradients, that's a topic for another course, but we'll give enough intuition that if you already know how to calculate gradients, you'll be able to understand policy gradient algorithms. We can't calculate the gradient optimally for a policy. We need to solve for all possible trajectories. Reinforce is an algorithm that samples trajectories similar to Monte Carlo reinforcement learning and then uses the results of those trajectories in order to improve the policy. Let's have a look at the algorithm here on the screen. Reinforce takes a differential policy as input and a Markov decision process and improves that policy. The policy that we put in is the same policy we get out, but with its parameters changed. Reinforce is similar to something like Q-learning or SASA. We repeatedly generate episodes until we reach some time limit or until we see very few changes in our policy. At each point we generate an episode, by following the policy pi of theta. So here the episode is in state 0. We select action A0, which gives us reward R1, until we reach a terminal state, which gives us reward RT. Then, for each one of the pairs in these episodes, we do the following. We calculate the future discounted reward from that step until the end of the episode, which is G, our familiar expression. And then we update the parameters in the direction of the gradient based on G. So you recall from the policy gradient slide, we saw this step here, except that at the end of the expression, we multiplied our expression by the quality of selecting action A in state S. Because we don't know what that is, because we're not learning it, what we do instead is we multiply it by G, which is our estimate of what QS of A is in that particular state. Therefore, what we can see that reinforce does is generates an episode, and then in each episode, it calculates the future reward that we receive from that step, and then uses that future reward as an estimate of the quality of the action and multiplies it by this gradient here. The vector will then be the direction in parameter space that increases the probability of selecting action A in state S in future. So we can see here that by sampling enough of these episodes and calculating these gradients, we will start to converge towards at least a local optima in our policy. So there's a couple of important things to note here about reinforce. The first is that when we select an action, we explicitly use the stochastic policy pi. This is unlike Q-learning and SARSAR, where we select either the best action and then we randomly explore sometimes, or we select according to some sort of softmax. When we do this, we're not doing the standard argmax calculation that iterates over all of the available actions to calculate their quality. Instead, we're using the policy directly. This gives us one huge example in that it allows us to have continuous action spaces. If an action space is continuous, that means we have an infinite number of possible actions that are available. For example, we might have an action where we rotate a particular number of degrees and that degrees is given as a real number. If we have an infinite number of actions, there's no way we could possibly iterate over all of them to find the maximum. In policy gradient descent, we use the policy directly to select an action probabilistically. Because the policy is stochastic, this means that we are both exploring and exploiting. Sometimes it will select the best action, sometimes it will select a weaker action. This is also going to be more efficient when we have a Markov decision process that has a large number of actions. So if we have to iterate over a very large number, that could be computationally expensive. Here, our policy takes care of it because it's stochastic. A second thing to note is the policy evaluation and policy improvement. Recall in policy iteration, we do an evaluation of our policy and then we use that information to improve the policy. Reinforce does the same. When we do policy evaluation, we generate an episode using our policy, and then we measure the quality of that using the return on that policy. Our second step here is our policy improvement step that uses this evaluation in order to update the parameters of our policy. A third point about reinforce is that it's a non-policy approach. We sample trajectories directly from the policy, and then we use those to update. The final issue is the issue of high variance or sample inefficiency that we see with Monte Carlo reinforcement learning. Because we're sampling over an entire episode, which is going to be somewhat exploratory due to the stochastic policy, we'll see variance in our future return G, the same way that we saw it with Monte Carlo reinforcement learning. This is because we're using G instead of a bootstrap value. Because we don't have a Q function or a value function in reinforce, we can't bootstrap like we do in temporal difference learning. However, later we're going to look at actor-critic methods which do mitigate this problem. Let's have a look at how policy learns in the grid world example. Here I have a policy that comes from implementing reinforce using the PyTorch deep learning package to represent the policy. We can see that the way we visualize the policy for grid world is different to value iteration and policy iteration because we have a stochastic policy. In the stochastic policy, we don't have the Q values of actions, but we have the probability that each action left, up, right, and down will be selected in this state. At the start, they're roughly the same probability. They're slightly different for no reason. It's just because we've got randomized parameters. But we see as we step through one episode, some of the probabilities update in our policy. So in the top right, where we've gained some reward on our first episode, it seems, the probability of going right has been updated. We've updated the parameters of our policy theta in the direction of the gradient, which would have said to increase the probability of going right. If we play through now the number of episodes, we can see the policy slowly improving through each iteration. At the end, as we reach towards a good policy here, the policy is still stochastic, but it's a lot better than what it was previously. In the bottom right, it's telling us to go up and then up again, and then right, and then right. And then here we can see the probability of going up and right is similar. That's because the value of going up and right are not that dissimilar in the end, because going up will bounce us back to this state. So the difference in value we see is just our discount factor of one move. We can see again that it's not a perfect representation. It's telling us the best action or the most probable action is to go up, which falls into the hole, because we're using approximation techniques in order to map the policy. In this implementation, because we're using deep learning to represent our policy and using the PyTorch implementation, there's no guarantee that this will converge to the optimal policy. It might get stuck in a local optima, which still looks okay, but it's definitely not the optimal policy. And in general, this will not converge to an optimal policy using any of these differentiable techniques. The sample efficiency problem with reinforce leads to issues with policy convergence. As with Monte Carlo simulation, the high variance in the cumulative rewards G over different episodes leads to instability. So if we think about how policy gradients work, they work a bit like this. An iteration of the entire loop is done in two steps. First, we generate a trajectory. We do this by taking our policy, pi of theta, it selects an action A, which is played into the environment. Then we add the reward from the state action pair into the list of state action pair and rewards that we are going to use later. Once we've generated an entire trajectory, step 2 is to update the theta in our policy by going over the state action rewards that we received over that trajectory. So we can see these two steps here are to generate a trajectory and update. We update theta based on G, the actual rewards we've seen, which is where the instability comes in. Actor-critic methods instead use a temporal difference estimate, just as we use temporal difference estimates in Q-learning and SASA. The architecture of the actor-critic method looks like so. As with policy gradients, our policy pi is used to select an action A. It executes this in the environment and receives a reward. What actor-critic methods do is maintain a value function or a Q function as well as a policy. After we've executed an action and we've got the reward in the new state, we update the Q function for that state action pair as well. We also use our Q function here to provide a temporal difference estimate on the future rewards from executing action A in state S. So the difference is that while we still use our stochastic policy to select an action A and execute it in the environment, instead of simply storing the new reward and observation, we immediately update a Q function or a value function of executing that action A in state S. And we use the same Q function to provide a temporal difference estimate to policy pi. This temporal difference estimate is used in place of G, our estimate for future discounted reward, and is going to provide more stability than using G because this is going to converge over time. The terminology actor-critic comes around because we call the policy our actor. It's the part of the architecture that decides which actions we're going to play and is the final policy that we really care about. Our value function, or our Q function here, is known as the critic. It provides feedback on the quality of these actions, but is not used to select the actions at all. Therefore, it's not an actor policy, it's a critic policy. These two work in tandem in order to help stabilize learning. Q actor-critic is an algorithm that implements the actor-critic idea. On the screen, we can see the algorithm. It takes a differential actor policy pi and a differential critic Q function Q and returns pi with updated parameters theta. We initialize the policies to our actor and our critic arbitrarily. Note that we use theta to represent the policy parameters and we use W to represent the Q function or critic parameters. This doesn't mean that the critic is a linear Q function because we're using the letter W like we did earlier. It's just we're using two different letters to differentiate the sets of parameters that we have. Our critic has to be a differential function just like our policy. At a high level, the algorithm looks a lot like SASA. We have a series of episodes, we select an action in each state, execute that action, and then observe the reward and the new state. We then select the action for the next state, and we do our updates. For the Q actor-critic, it's how we do the updates that differentiates it from policy gradients and also from Q-learning and SASA. These three lines here are the important ones for Q actor-critic. The first line looks much the same as our SASA update. We calculate our delta value, which is the reward plus the discounted future reward estimate that we get from our Q function. And then we subtract the old value as well. Then we update the parameters of our Q function, the critic. We do this in much the same way we would do it in Q-learning. Note that we have a learning parameter alpha W and a learning parameter alpha theta. That's just so that we can learn the critic and the actor at different rates if we want. We could set these to be the same value, but we have two variables for this. So we update it by taking the old weights and then weighting them 1 minus alpha W and then weighting the new information alpha W. That new information is just our temporal difference estimate that we receive here and multiplied by the gradient of our Q function. We've seen that before. The new line is the way we update the parameters of our policy pi. That's our actor. To update the parameters, we take our old theta value plus our learning rate, multiply it by our temporal difference estimate again, and then multiply that by the gradient of the log of the policy. This is much the same as the update in the policy gradient method, except that instead of using G, the actual rewards we got on this episode in the future, we use our temporal difference estimate that uses our Q function. So this line here just calculates our delta as we have before. This line updates the weights of our Q function, the critic, and this line updates theta, the parameters to our policy. Each of these updates using the gradients, and this is a policy gradient update that just uses a different estimate, delta, which is at the temporal difference estimate, instead of G. Wait. Didn't we say earlier that the weakness of value-based methods such as Q-learning was that they couldn't extend to things like continuous action spaces because they were using a Q function? Haven't we now just gone backwards by including a Q function? Why don't we just use the Q function directly and go back to Q-learning if we have to learn a Q function? Yes, that is a weakness of value-based methods, but let's think of it. Why were the value-based methods unable to work in continuous action spaces? Because they had to iterate over all actions and find the one with the highest Q value when they were exploiting. That's right. What selects the actions in the Q actor-critic algorithm here? The policy actor pi selects the actions. Right. So that doesn't have to iterate over all of the actions. It's a stochastic policy that's learnt to select actions in a stochastic manner. What does the critic Q function do in actor-critic methods? It provides feedback on the selected action and provides a temporal difference estimate. Right. So why does this work in continuous action spaces now? It's because the actor policy does the selection of the actions and the critic merely provides feedback in order to calculate the temporal difference estimate. And we never have to iterate over all of the actions to select them using the Q function. Exactly. In this part, we looked at policy gradient methods. These are model-free, policy-based reinforcement learning methods. We briefly looked at the policy gradient theorem that makes policy gradient approaches possible. We then looked at the reinforce algorithm that uses this directly to update the parameters of a policy based on some samples it's taken in the environment. We then studied actor-critic methods which overcome a key weakness of reinforce, sample efficiency. Policy gradient methods are key in many successful reinforcement learning solutions, including multi-agent solutions. We're going to look at multi-agent reinforcement learning next, so stay tuned.